Coming up on Dr. Kiki's Science Hour, we're talking about the science of acoustics and bubbles with Professor Tim Leighton from the University of Southampton in the UK. That's up next on Dr. Kiki's Science Hour.
Netcasts you love.
From people you trust.
This is TWiT.
Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with me, Dr. Kiki. Episode number 139, recorded Thursday, April 5th, 2012. How do we sound? This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Welcome, everyone, to Dr. Kiki's Science Hour. I am Dr. Kiki, and this is the show where you get to spend an entire hour digging into a single subject in the sciences with an expert in that topic. And I hope you're ready, because today we're going to dig deep, get dirty in the science of sound, answering interesting questions like, how would we sound if we found ourselves on Venus? Or how do we sound to our goldfish? These are very important, pressing questions, but not the only things that Professor Tim Leighton, our guest today, works on in his acoustical studies. But before we get into the interview, I, as always, have a few science headlines. It's April 5th, 2012, and these are the science stories that made headlines this week. The half-life of samarium-146 has been revised by physicists working at the Atlas Accelerator Facility from 103 million years to only 68 million years. So what does this mean? Well, since samarium-146 is used in geological dating, it will change the dating of some major geological events on Earth and other terrestrial planets and impact models of solar formation. A very well-preserved woolly mammoth carcass was found in Siberia by tusk hunters. Scientists who acquired the specimen say that there is evidence of human interference, but it's as yet unknown whether the actions were taken 10,000 years ago, shortly after the animal's death, or more recently. Additionally, the color of the mammoth's woolly coat is direct evidence that the furry beasts were closer to blondes than brunettes. A fossil found in northeastern China hints that T-Rex might have been fuzzy rather than scaly. The remains are from a T-Rex relative named Eutyrannus huali, meaning beautiful feathered tyrant, who lived about 125 million years ago. The finding has paleontologists rethinking the entire Tyrannosaurid family in a more feathered way. Remains of a crazy, gigantic snake were found in a Colombian coal mine dating to about 58 million years ago. The snake, called Titanoboa, measured around 50 feet long and weighed more than a ton. A life-sized replica is now on display at the Smithsonian Natural History Museum. Human activities are the cause of declining Caribbean coral reefs. Recently, the decline has been linked to climate change due to humans, but a study out this past week in the journal Ecology Letters by researchers from the Scripps Institute finds that humans have been directly damaging Caribbean corals for far longer. Reconstructing a historical timeline of reefs, they qualitatively show that deforestation and overfishing were deleterious as far back as the 1800s. Publishing in Nature this week, climate scientists present evidence that carbon dioxide increases in the atmosphere predated increases in temperature that brought the last ice age to an end. The study relied on climate proxy data from 80 locations around the globe, including over 14,000 years of climate history. While highlighting the role of carbon dioxide in such major climatic shift, it does not address the source of the carbon dioxide. We still don't know where that CO2 came from. And identical twin data suggests that our genes are not the places to look for telltale signs of disease risk. A study published in Science Translational Medicine looked at genetic data from over 50,000 twin pairs, finding that only 4 diseases were predicted reliably. Lifestyle, environment, and random chance are far larger factors than genes in most disease determination. Researchers publishing in 2 journals, Environmental Science and Technology and Science of the Total Environment, found that factory farms feed their chickens caffeine, banned antibiotics, antihistamines, anti-inflammatory agents, and arsenic. The studies analyzed feather meal, which contains a record of compounds a bird has been exposed to, similarly to using hair to test for drugs in humans. Since the experiments didn't analyze meat, it is still unclear how many of these compounds are being ingested by people. An international team of researchers created a solid-state 2-qubit quantum computer inside a diamond. Using impurities in the diamond to their advantage, the engineers used microwave pulses to continually switch the direction of electron spin and reduce the likelihood of decoherence, or introduction of errors. The computer functioned at 95% accuracy. MIT professor Daniela Rus wants to democratize robotics. The GRASP project received $10 million in funding from the National Science Foundation to create printable, programmable computers that can be created by the average person in a matter of hours. Brain scientists used positron emission scanning to image the brains of people as they awoke from the effects of anesthesia. They found that activity in the brain correlated with the return of consciousness first showed up in the more primitive brain areas like the thalamus and limbic system before occurring in the neocortex. The researchers think this suggests that a, quote, foundational primitive conscious state must be restored before higher order consciousness can occur. Senior reviews of 9 NASA missions found all to be successful and awarded funding to continue operations until at least 2014. The Fermi, Swift, and Kepler missions will be funded through 2016. Hubble and Chandra are to receive continued funding. Planck's low-frequency instrument is extended for 1 year. Spitzer will close out in 2015, and Suzaku and XMM Newton are extended through 2015. The Large Hadron Collider went back to work this week with a boost in its operating power. 2 beams of protons were collided at a world record total of 8 trillion electron volts. Increasing the power involved in these subatomic collisions increases the possibility of finding as yet unseen particles like the Higgs boson. In an update to the faster-than-light neutrinos story, the Italian scientist who coordinated the OPERA experiment at CERN has resigned. His faster-than-light result was reversed after process errors were discovered. And that does it for the science news headlines this week. Let me know what you think about these science news stories, or tell me what you think should be science news by emailing me, Dr. Kiki at drkiki.tv, or you can leave me a voicemail at 650-741-5454. Now it's time for a word from our sponsor. Thank you, Netflix, for sponsoring this episode of Dr. Kiki's Science Hour. Netflix streams thousands of TV episodes and movies directly to you, saving you time, money, and hassle. Which means there are several easy ways to access instantly these streaming movies and TV shows on Netflix. You can watch them using your Mac, your PC. If you have an iPad, there's an iPad app. There's an app for the iPhone, and there are even apps for some Android devices. Additionally, you can watch on gaming consoles like the Xbox 360, the PS3, or the Wii. If you don't have a gaming console, but you have a set-top box, or maybe you're interested in getting something like the Roku box or an Apple TV, you can watch on one of these devices very easily. It's a simple interface, and these devices are pretty cheap, easy to use. With Netflix, you can watch movies, TV shows instantly using any of these devices, and you can start on one device, stop at any point for whatever reason you might have, and then pick up watching where you left off on any other device. It's a seamless experience. Whichever way you choose to access Netflix, you can watch as many movies and TV shows as you want anytime you want. So it frees you from the schedule of a television. And you can cancel at any time. Try Netflix today. They're offering you a free 30-day trial if you go to netflix.com/twit. That's right. Use this URL. Go to netflix.com/twit. Try them out. Free 30 days. See if you like them. Be sure to use this URL, netflix.com/twit. And we'd like to thank Netflix for their support of TWiT and Dr. Kiki's Science Hour, and hope that you enjoy watching instantly with Netflix. Excuse me, I've got a little bit of a frog in my throat. I'd now like to bring our guest for the show today into the show. Professor Timothy Leighton is a professor of ultrasonics and underwater acoustics at the University of Southampton in the UK. He's chairman of the Fluid Dynamics and Acoustic Research Group and deputy head of school research at the Institute of Sound and Vibration Research. He's also a founder of the Center for Ultrasonics and Underwater Acoustics. Professor Leighton, thank you so much for joining me here today.
Thank you.
Yeah, it's great to have you on. I know it's rather late for you in the UK, thanks to our wonderful time difference. But it's great. I'm glad you're taking the time to join us in the middle of the night.
Thank you.
So I was looking down the list of research projects that you're involved in, and I found that a lot of them have to do with bubbles.
That's right. That's the main thrust.
Yeah. What got you interested specifically in bubbles?
I got interested in bubbles in the late 80s when I was about 20 years old. And I was wondering what causes babbling brooks to make a babbling noise. We know that brooks and streams are musical, and this inspires poets to write poetry about them. But the question was, why do they make these noises? And it turned out to be primarily due to the bubbles in them. Now, I'm talking here about balls of gas surrounded by liquid. Not children's soap bubbles,
right.
Which are gas surrounded by liquid surrounded by gas. So I'm talking about bubbles underwater. And it turns out these bubbles are like little bells or gongs. When they're formed in a stream by a splash or something, they're trapped, balls of gas trapped underwater, and they ring like little bells. So a small bubble will give a high note, blink, and a little bubble, and a large bubble would give a low note, a plonk. It's a bit like we're used to hearing scuba divers give out blub, 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 low notes when they breathe out bubbles.
Right.
But if you hear your dripping tap at night, dripping into a sink, it gives out a very high plink, plink, and that sound is a result of tiny little bubbles being produced. So we worked out that when a stream produces these bubbles, it produces these sounds, and the maths and the physics just and so balance up so that the notes they produce are in a frequency band that we humans can hear. If the maths and physics had worked out a little bit differently, then the brooks and streams would have been silent because the sounds would have been outside of our range of hearing. But fortunately, those maths and physics were just right so that we could hear them. And we've taken that on now. For example, to go out, we now 20 years later, we're going out to the oceans, and we drop large pieces of equipment, perhaps the size of telegraph poles, over the side of ships, and they listen to waves breaking. So now whenever a wave breaks in the ocean, it makes a loud noise, and that's because it's trapping a billion bubbles at a time, all of different sizes.
Yeah.
Now each of those bubbles sings once. It sings its note that's related to the size it is. And so it's a bit like a choir of people, each got their own note. They just sing it when the wave breaks. And from the chorus of notes we hear, we know how many bubbles were produced and what size they are. And that's important because when a bubble is produced by a breaking ocean wave, it's trapping atmosphere gas, and then those bubbles dissolve. We know that happens. Bubbles dissolve. So it's a way of getting atmospheric gas into the oceans. Now, we know about 1,000 billion tons of atmospheric carbon alone transfer between the atmospheres and the oceans. So when you try and do climate models of the carbon budget for the planet, when you're looking at climate change and such like, it's very important to include in those models the amount of gas that transfers between the atmosphere and the oceans. And one of the inputs to that is done by counting the bubbles in the ocean that are produced by breaking waves. So that's where that particular thread of research has taken us in sort of the 20 years that we've spent on it.
Yeah, it seems like such an amazing storyline to go from wanting to know how a bubbling brook makes the sound, the musical sound, to the much larger issue of actually atmospheric gases getting into the ocean. I hadn't ever actually considered it in that sense. I just always thought of it as a static water surface, and there's maybe diffusion across the surface of the water. How do you? How many billions? How big a scale of bubbles are we talking when you start calculating this kind of a thing?
You mean how big are the bubbles themselves?
Or how big are the bubbles, and then, because there's got to be a large range of bubble size, and then how many bubbles are in the ocean?
That's a good point. When it comes to sizes, we know that they go down to definitely less than 10 microns in radius, probably much smaller, and then they go up to centimeters in radius. But of course, there's a sorting effect because the big bubbles rise quickly under buoyancy, and therefore, although they could be formed by the breaking waves, they tend to come out of solution, out of the water very quickly. Whereas the little bubbles will hang around in time because the buoyant forces aren't making them rise so quickly. And so, because there are currents and turbulence pushing them around, they persist in the water for quite a while. I have to say, I'm not the only person in the world studying this. There's probably 100 or so or more scientists around the world look at bubble formation in the ocean, and it has. You're absolutely right when you say. That the initial consideration is of the oceans as a flat, unbroken surface, because that's where most of the calculations have been done when they've been trying to work out how much greenhouse gases dissolved and come out of the oceans. And it's only perhaps in the last 10 years or so we've started being able to get numbers on the amount of that transfer that's caused by these bubbles, and the bubbles probably double it, though the numbers aren't known exactly. They probably double the annual exchange of gases, both because they break up the surface, so they give you a larger surface area, but also because they actively, if you like, pump gas into the oceans. Because when you form a bubble, surface tension makes that bubble dissolve away, and so that's pumping the gas into the oceans.
Is there a lower limit on the size of a bubble? You said that the smallest is probably about 10 microns. Is that because the physics of the bubble formation don't really allow them to form any smaller?
That's a very good point. If you have a large bubble, it can easily break up and deform in order to produce two daughter bubbles, which can then break up and deform and so forth. Now, because of surface tension, the gas pressure inside a bubble is greater than the pressure outside. And the difference in the amount by which it's greater goes up, the smaller the bubble is. So a big bubble is easy to deform and break up. It's like getting hold of a football that's only, weakly inflated. And so it's easy to deform that. And so a centimeter-sized bubble easily breaks up. It loses its spherical shape and breaks up. Now, by the time you get down to a 10-micron-sized bubble, the gas pressure inside is much greater than the pressure outside. And so it's like having a football that's been pumped up really tight. It's very hard to make that deform and break up. So it's harder to break bubbles the smaller they go. But this gas pressure means that this excess gas pressure inside means that they're dissolving more quickly. So as they get smaller, there's a greater the speed at which they dissolve becomes greater and greater and greater, and so they dissolve away. And if you calculate how long bubbles will stay in exist in solution, then the initial calculations tend to say that after a few minutes these tiny ones will have disappeared. But we know that isn't true. We know they hang around for a lot longer. And the reason for that, I think there's two reasons. One is that the surface becomes, as they get small, then there are contaminants in the ocean. There's, the chemicals left over from, obviously, man-made activities, oils and things, but also from the activities of life in the ocean, plankton and such like. They all produce oils and things like this. And these gather on the surface of the bubble. Now, as the bubble gets smaller and smaller, they become, more and more strong in concentration. And so they will resist the bubble getting any smaller. To make the bubble get small, you have to start making these molecules line up in order, and they don't like doing that. And the other reason they don't dissolve away is I think they start attaching to small particles of grit or solid in the ocean. Mm-hmm. Now, that stops bubbles dissolving away. If you look at the glass of water you have by your bedside table, it can be clear in the evening when you go to bed, but in the morning you've got lots of little bubbles around the side of that glass. And what's happened there is that the small bubbles that were too small for you to see when you went to bed, they've all risen up out of the water or dissolved away. They've gone. But any little cracks and crevices in the wall, in the glass, then those bubbles haven't tended to dissolve away because the glass has stabilized them. So they've just sat there. Now, during the night, your room gets colder, and more gas dissolves into the glass of water. Mm-hmm. That's fine. You don't see anything happening there. But in the morning, your room starts heating up, and that causes gas to come out of solution, and they find the little microscopic cracks of bubbles trapped in the cracks in the glass wall of your overnight glass, and cause them to grow. And that's why you see bubbles, a millimeter or so in size, sticking to the wall of your glass. They're clues to where the cracks are in the glass because they've grown out of those cracks. And once they get big enough, or if you shake the glass, they'll come off in the morning.
Right. And the extreme of this is the whole Coke and Mentos experiment.
Yes, that's right. And the Mentos puts chemicals into the water, but also provides a lot of little areas of surface and grit for these bubbles to find and grow from. Exactly.
I'm just fascinated at the extent of bubbles. How interesting bubbles can be. This is just fantastic. What else in terms of in one of your research lines is the improvement of sonar detection in bubbly water?
That's right.
And you don't mean fizzy water that you get at the restaurant. I'm assuming that you're looking at something like sonar detection in the ocean that probably be used by a navy.
That's right. Bubbles, as we've said, are very good at generating sound. When a wave breaks, they produce a lot of sound. Now, anything that produces sound, if you shoot sound at it, will wobble back at you. If you go up to a guitar and shout at it, the strings will rattle. If you go up to a piano and you press the sustaining pedal down, you shout at the piano, it'll hum back at you because each string will oscillate in sympathy. So they're very good at scattering sound. Now, in sonar, you're sitting there underwater and you're trying to send out sound pulses and find where targets are by looking at the echoes that come back at you. And it's a well-established technology. Now, if you're and it's used by humans, it's used by dolphins. Now, in areas where there's a lot of bubbles, the problem is the bubbles also scatter sound off you. So if you're a dolphin and you're looking for a fish, then you're looking for the echoes scattered back from the fish. But if that fish is in bubbly water, then you get a lot of what we call clutter in the sonar from scattering from lots of bubbles, and it's very hard to find where the fish is because it's hidden amongst all the bubbles. On the human side, we might look at if the military are trying to do a mine clearance operation, they're trying to find mines, then if it's in very shallow coastal waters, you've got a lot of bubbles generated by the breaking waves as they approach the shore. And again, that can look like, that can produce clutter to our sonar in exactly the same way as, for example, if you're driving through fog in your car and you put your headlights on, the little droplets of water in the air will scatter the light back at you and give you some kind of clutter and glare. In the same way, underwater, when you send sound out, the bubbles there will give you scatter back to you, cluttering the image. And so we know this is a big problem. But for example, in the Gulf, if you wanted to, there's been a lot of military activity there. There's quite a lot of there's been quite a lot of ordnance there. We know that we desperately wanted to get in the last 20 years. There've been times when there's been we know there's been hostile activity on shore, and we wanted to get ships, merchant ships, humanitarian aid in. And all it takes is the suspicion that there is a mine or something out there to slow down the whole operation, because you've got to find that. And it's very hard to do if there's a lot of bubbly water around.
Right, especially as you get closer into shore, there are going to be waves breaking. There's going to be a lot of bubble formation.
That's right. And we know that there comes a point when there's so many bubbles, you run out of options. Divers would have to go and feel with their hands, or dolphins would be sent out. We know that, and that's an interesting topic, because we know that if you take a dolphin and you look at it as a piece of machinery, sonar machinery, in a way, it's not as good as the best human sonar. It's not got as much power in its acoustic signal. Its frequency range isn't as great as humans can use, and yet it can operate in bubbly water where the best human Navy sonar can't. Obviously, it's got some other advantages. It's a moving platform, we say. It can swim around and look at a target from various angles. We know that. Right. But also, it's got a huge brain sitting there operating this sonar thing. And whilst we've been using sonar in the oceans for perhaps 100 years, this thing's evolved over 10 million years using its sonar.
Yeah, it's probably something very similar to humans being able to tune into the voice of a friend in maybe an environment that's a little bit noisy.
Exactly.
So there's a lot of just sound noise around you.
That's right.
And so a dolphin has evolved to tune into its sonar environment in a very similar way.
There is something, and it obviously comes from the fact that it's been immersed for so long. Now, I saw a BBC film in about 2001 of some dolphins hunting for fish, but they were blowing nets of bubbles in order to trap those fish. And the way they do it is from their blowhole, which is produced from one of their nostrils, goes to the top of the head, and they can produce bubbles from it. Now, as soon as I saw that, I thought to myself, there's something here I don't understand, because either I know that if the dolphin's sonar ability didn't exceed our own, then they would be blinding their superb sonar echolocation exactly at the point when they're hunting. So I said to myself, okay, they must be doing something else. Either they're blinding themselves or they've got a sonar ability we don't know about. Now, in the UK, we can't do experiments in tanks on dolphins. It's the Queen owns them all. It's illegal for us to do that. Right. We can't put them in zoos or anything. So we didn't have any options. So I had to sit there and think. And it was a fun exercise. I thought to myself, how would I design a sonar pulse if I was a dolphin in order to see a target, a fish, amongst all these bubbles?
Right.
And what we worked out was there was a kind of pulse, and it's by sending two pulses in close succession. And they are identical to each other, but one is of opposite signs. So if one pulse comes out as a +1, if you want to think of it as a number, the other pulse is a minus. Sorry, I'm confused where the camera is. The other pulse is a -1.
Right.
And we did some computer simulations, then put this in a tank, and we tried to see it with a sonar source and built a sonar source, see whether it could work. And the way it works is this: if you send out these two pulses, +1 and -1,
they're going to completely negate each other.
Yeah, when they come back, if you add them together in your head, then or you get the computer to do it in this case, then any scatter from a target, a fish or a mine, goes to 0, because exactly it's a +1 added to a -1, so they go to 0. So you cannot see the target. But bubbles scatter a lot of energy, not at the square. They square the number before scattering it back. So when you add the pulses from the bubbles together, you have +1 +1 squared, which is 1, plus the square of -1, which is also 1. So they add together to give you a strong signal. Right. So that way you can, if you add these two pulses together, you hide the fish and see the bubbles. But if you take the same pulses and mentally you subtract them, then the signal from the bubbles is 1 squared minus -1 squared, which is 1. We give you nothing, so you don't see the bubbles. But the signal from the target gives you a 1 squared minus a -1 squared. Sorry. Getting myself confused. Yeah, it gives you 2. So you get a strong scattering from the target. So that way, you send out 2 pulses, and you mentally add them, and you see the bubbles and not the target, or you mentally subtract them, and you see the target and not the bubbles. And mentally, you can flash between the two, and you'll get whatever's the target is the little thing that's flashing. So we worked that out, and it works as a piece of hardware. Of course, there's no proof that the Dolphins are doing this, and I have to say, this technology it's known about for biomedical purposes. So what we then did was we took it out to sea and looked in ship wakes, tried to find targets in ship wakes, and it worked very well. We then tried to find whether any dolphins use this kind of pulse, and so we colleagues around the world who do examining, go out and record what sounds dolphins make in the wild, they were finding pairs of pulses that were resembling this, but none of them were powerful enough to make it work. So we were kind of close, but no cigar. We've got a sonar that did the job, and it seems like dolphins weren't doing that. Right. But what we've done since, and we haven't published this yet, is we have gone and started using real dolphin pulses in a similar way of processing, mental processing, if you like, doing the maths. And we have got that to work now. So we've built the world's first sonar that could detect targets in bubbly water, mainly by trying to think like a dolphin, and eventually we've converged on a solution that, say, it's a technology that works.
I think that's fantastic. The use of the biological example to be able to get to a technological solution. I think it ends up becoming a very elegant way to get to the answer of a problem.
Yes, yeah, it makes a nice story, and it's always nice to be able to think that I've spent all my adult life trying to think of sound underwater, and it's nice to kind of think about these dolphins who've spent all their lives, and how we might approach the same problem differently. And it's nice to try and get into to see how nature is trying to solve the problem that you're trying to find a solution to.
Yeah, see through the sonar of the dolphin.
That's it.
Not necessarily the eyes. So people in the chat room have been wanting me to ask about this. I don't know if because it has to do with underwater sound, the bloop. Do you know about the bloop?
I'm afraid not.
It's the loudest sound recorded by the U.S. Navy in 1997. Some very loud underwater sound that has no known explanation to this point in time, at least according to Wikipedia.
Okay. No, I'm not familiar with that terminology. I know that there has been there has been something called a 20 cycle pulse, which might be it might be what they're talking about, maybe not. I've not heard of the terminology of the bloop. I know the 20 cycle pulse mystified people for quite a while because it's a very deep, very powerful acoustic source that seems to move. It's called 20 cycles because I think it's at 20 hertz. It goes on for a few minutes, goes quiet, continues again, and that was mysterious. But I think that's people are now thinking that might be something to do with whale navigation. Some people have said whale heartbeat, but I think that's the latest explanation that I've heard of that. But I don't know if it's the same thing. But I know that there's a great deal we just don't know about the oceans. You know, there are whales, you know, mammals like us who will dive down to 2 kilometers and stay there for several hours, and then even sleeping there and coming back up and then doing a few shallow dives. These are called beaked whales, and they go down again 2 kilometers and swim along there and come up, and they, if undisturbed, they don't suffer the bends. Now, that just amazes me that creatures can do this, right. Because their lungs will collapse completely beyond a certain depth, and then they just keep going. They do it to get food. Now, we don't understand how they're surviving that. At least I don't. The research I've read doesn't seem to reveal that. We're investigating it. We're trying to get clues in how they possibly survive this kind of experience and do it out of choice. I guess there's they aren't the biggest of whales, but they do it because the competition for food isn't so strenuous down there. They found a niche that they can do. But the fact that a mammal, air-breathing mammal, can go to 2 kilometers depth for hours at a time, that it chooses to do, astounds me.
It's got to be the bubbles of gas in the blood, right? Saving up, or in the lung, just saving up little pockets of gas somewhere.
I think they're saving up gas. I think if it comes out, it's got to be dissolved. Once it comes out of bubbles at that once it comes out of solution, right, out from being dissolved into bubbles, when they're changing depth. Then you've got a problem because you're going to get the bends. Because you've got to understand. That's the problem
with nitrogen in the blood leading to the bends in humans.
That's right. You know, the pressures are astounding. You know, people. I guess we're going to talk about space later. And we think of space being a vacuum. So the difference in pressure between us here on Earth and going to space is 1 atmosphere, 1 bar. Now, you get that change in pressure for every 10 meters down you go in the ocean. And so the difference in pressure when you go to the ocean deeps dwarfs the change in pressure that you've got to withstand when you go into space. Again, it's a mind-boggling piece of biology that they can survive this. But if you have bubbles forming in the bloodstream at those depths, then or as you rise up, then you've got real problems. I don't see how that would be survivable.
Then they somehow block the formation of bubbles.
They somehow block it. Yeah. We don't know how.
Huh. So when I think of bubbles and acoustics, I mean, I think of, sound, and I think of just simply the way that most people interact with sound on a daily basis, not anywhere beyond that. But you take it to really interesting places. Cousteau Electrochemistry.
Oh my goodness!
Can you tell me a little bit about what this is and what you're working on there?
Okay, I mean, I trained as a physicist and I work in an engineering faculty, and so as a physicist, I tend to take things from their fundamentals. I like to start with a blank piece of paper, check that whatever I'm going to be working on starts from Newton's laws of thermodynamics, something straightforward and simple, and it's fundamental. And that way, I work through a problem, and it's a good scientific approach because it does mean whatever problem you're trying to get to, you solve that problem. It's not a bad way of doing engineering, I guess, is to have a few solutions and try and make every problem fit that solution. That's a bad way of doing it. I like to start at the fundamentals and move towards a solution that's the right one for the problem that's facing me. And I like to, because I deal with sound underwater, I like to see how far it takes me in various directions. So that means working with other people who are experts in their field. So, we can work with archaeologists looking at sonar that will look at wrecks that are buried in mud and invisible underneath the seabed, getting sonar that will penetrate that seabed and see them. We can work with medics, zoologists, and perhaps my most rewarding collaboration has been with a chemist, Dr. Peter Birkin at the University of Southampton, who's currently doing a sabbatical over in the States in Utah. So anyway, he's a chemist, and an electrochemist, and that means he looks at the way currents are generated and formed when electrodes are put into liquids. Mm-hmm. And if you put electrodes into liquids, that's the classic way of producing a battery. Yep. But it's also a way of sensing things. Because if I have two electrodes stuck into a conducting liquid, and I put a wall between them, and the current can't flow between the two electrodes, then I can sense that the wall is there. So that's electrochemistry, as far as I understand it. Anyway, I'm speaking. I collaborate with people who know a lot more about electrochemistry than me. Anyway,
it's also a principle. You can stick the electrodes into not just liquids but living cells and be able to get. If you have an electrode on one side of a cell membrane and an electrode on the other side of the cell membrane, you can observe the current, measure the current that goes across that cell membrane.
It.
So neurophysiology, electrophysiology is that use of the technology.
Yes. Yeah. So Peter, in fact, and I got together about, 15 years ago now. And he was young, and I was younger than I am now, and quite excited about how we could put his chemistry and my physics and acoustics together. And we started building instruments and devices whereby you get an electrochemical solution and you put sound on it, and you see the way that affects the electrochemistry. So, for example, we could use this. I'm just trying to think. We could use this to look at erosion. Now, if you're trying to look at the erosion of something underwater, normally, which is very important in pumps, oil companies spend billions on this kind of thing. It's important on shipping, all these things. If you're trying to look at erosion underwater, generally, you have to let the thing be eroded, the propeller, say, and then take it out, look at it under a microscope, see what damage has occurred. And if you want to test an environment, you have to maybe put a sacrificial piece of metal in eroding environment, leave it there for a few days, and then weigh it and see how much mass it's lost. So this is a very kind of slow, macroscopic, clunky process. And what we wanted to do was be able to measure really fine-scale erosion down to 10 nanometers, say. 10 nanometers. So that's 1/100th of a micron. Say we wanted to measure erosion on that scale in real time, because you could then measure erosion for things like medical devices, and you get a real-time measurement of what erosion is happening. So one thing that we did is we took little electrodes. So imagine this is a rod, an electrode here, and it's aluminium. Well, if you put aluminium in water, what happens, it doesn't stay shiny aluminium for too long. It forms very fine layer of oxide on the surface, aluminium oxide, the aluminium equivalent of rust, if you like. It's only 10 nanometers thick. It's very thin, but it's the thing that means that aluminium stops being shiny and has a more of a dull sheen on it. And that can sit there. And if erosion happens, the first thing that happens is that thing is moved off. Now then, the next thing that happens, because you've now got clean, new, shiny aluminium next to water, is it grows again in a few tens of microseconds, so not very long. That grows back. It heals itself, self-healing. Now, to heal itself like that, it's an electrical reaction. It needs current. So if you put a wire on the end of this electrode, then you can measure the current required to heal that surface. Now, it's very small. It's microamps or less. But what you can do then is build an array of these sensors, and they can each be, 100 microns wide. They can be embedded in a material, and then you can put that material inside your device that you want to monitor the erosion of. And as it gets eroded, all the time that it's being eroded, you're getting these oxide layers rubbed off, and new growth in fraction of a second, and you can monitor that by the very small currents. So what we could do, for example, is generate erosion by putting powerful ultrasound in to a liquid, getting bubble collapse. It would clear the surface off this thing, the erosion sensor, and then we could watch it regrow. And so now we've got a really wonderful way of in real time measuring erosion on a very fine scale. So you could embed that into propellers. You could use it as a sensor when you've got fine ancient watches and are cleaning them and are trying to make sure that you're cleaning just enough without eroding the actual substrate. You can put them in computers and microchips when they're putting in ultrasonic cleaning baths to be cleaned. And you can do all these things just to make sure that the amount of cleaning that you're doing is not eroding and damaging the surface. Right. So we've built that kind of sensor. So that's an example of Cousteau Electrochemistry.
I think it's fabulous, and you won an award from the Royal Society for innovation for this. Is that?
That's correct? Right. Yeah. That's right. Peter Birkin and I were given the Brian Mercer Award of the Royal Society, which was really good because it was for an ultrasonic cleaning technology, because we were trying to make things wonderfully clean without using much water or cleaning fluids, surfactants, or power. Now, if you are trying to get something clean, you've got a number of options to do this. One is the ultrasonic cleaning bath, which is very familiar in jewelers. And it looks like a little tub, and inside that you dip your device to be cleaned. The problem is the thing to be cleaned has to be small enough to fit into the bath. So you have to be able to take the thing and put it in the bath, and it has to be small enough to fit in there. So it's no use going up to your engine in your car and trying to clean away with it. Right. For that, you use a hose, a power washer. But the problem with power washers is they use an awful lot of water, an awful lot of surfactant and cleaning fluids, and they generate an aerosol of fine drops. Now, you might not be too worried if you're cleaning your engine that way, but if you're cleaning out a sewer line that way or a nuclear power station, you don't want fine drops of contaminated material. Right. Also, the power washers, they use a lot of electricity, and they're very hard to scale up. If you imagine somebody holding an array of 100 by 100 of these power washers, they'd be pushed backwards. So what we developed is to put the power of the ultrasonic cleaning bath on the end of a gentle stream of water like you get from a tap or a hose. So you can take it up to your thing to be washed and hose it down, and it cleans it, wonderfully well. It uses about as much electricity as a light bulb. It uses very little additives. In fact, with the latest generation, all we put in there is a little bit of salt, about a quarter of the concentration you get in seawater, a little bit of salt in there, and so the runoff water is very easy to clean up. It doesn't contaminate your groundwater supplies. You don't spend a lot of money on surfactants. It works with cold water. So you're not spending a lot of electricity bill heating the water up.
Yeah.
So it's good. It saves water. It only uses about 1 or 2 liters a minute, which is very low flow rates. And so this was an idea that you can, being on a hose, you can take it to the thing to be cleaned, whether it's a vehicle or a building. And so this was the and we're also developing. We've got a low power version where you can clean your hands. And there we're interested, for example, in making sure foodstuffs are cleaned. If you remember a year or two ago, there was a big, in Europe, there was a few deaths from a big problem with cleaning bean sprouts. Yeah. Cleaning vegetables is difficult. Cleaning pesticides off vegetables is difficult. We don't want, becoming more and more aware that the pesticide load on these things can be hazardous to health. Yeah. So we've developed a low power version that's safe for hands, and we're hoping that will be developed for washing for in hospitals, so that we can get rid of these hospital-acquired infections, and so that we can wash foodstuffs and get the pesticides off them and get them clean for the home. So we've got that device, and the Royal Society awarded us. It was £250,000, which is very useful because we'd been kind of putting. We're not going to spend it on ourselves. We've got staff that we hired and that worked with the researcher Doug Offen. He worked his socks off for years trying to develop this with us, and it provides salary for him and some more assistance. It buys equipment, and so. And as I say, it was very welcome because we'd been trying for years to get this funded from government funds and industry, and just never people weren't quite getting it. They weren't quite seeing what it would do. And then the Royal Society saw it and said, aha, this is the thing. This is the one thing we want to back with this award this year. And so they funded us to do that. And we hope you'll have these in every home before too long.
Well, congratulations on that, and good luck. It sounds like an amazing innovation to be able to, like you mentioned, hospitals, and that is a huge problem. And currently doctors have to wash their hands for 2 minutes or over to make sure they're scrubbed, and then they wear the gloves. And health and sanitation is a huge issue, and to make it easier would be great.
Yeah.
But we need to talk about space before we get to the end of the show. One of the main reasons I wanted to talk to you today was there was a press release this past week about some work that you've been doing on the side with all of your what I'm noticing has got to be very free time from these projects that you work on. A project working with the British Museum to be able to allow people to hear what it would be like to be on other terrestrial planets. Can you tell me a little bit about how you got started with this project? And then I want to move into listening a little bit.
Great. Okay. I got interested in about 2003 on this because I knew that there was a mission that was going to send a probe called Huygens to Saturn's largest moon, Titan. I think it was a European probe, but it got there from on a NASA rocket called Cassini, and Cassini's still out there orbiting Saturn, taking wonderful photos. And Huygens was hooked on the side of Cassini, and they flew together for 7 years to get from Earth to Saturn, and then Huygens kind of disengaged and fell towards the moon of Titan and parachuted through the atmosphere of Titan to see what was there. Now, Titan's a fascinating world. It's a very big moon, but it's got a thick atmosphere around it, and that's because it's so far from the sun. It's cold. The surface temperature is 180 degrees Celsius below zero. Right. And it's very cold, so that means the atmosphere hasn't been boiled off. So you've got a thick atmosphere around there. That atmosphere is mainly nitrogen, so in that respect, it's like our own. The atmospheric pressure at the surface of Titan is about 50% greater than the pressure on Earth. So in that respect, it's very similar. Where it's different is the fact that it's extremely cold, and it's full of all sorts of other chemicals in smaller proportion. And these chemicals produce a thick smog around the planet. And so until we'd actually gone there, no one knew what the surface of Titan was like, because you couldn't see through this smog. And so this was the excitement about Titan. It was a completely blanketed, undiscovered world. The chemicals that are available in the smog were not dissimilar to the soup that was available on Earth when life first started. Now, I'm not saying that there's life on Titan. It's far colder, much colder, but the chemicals are there. And if you get a lightning strike or a meteorite impact, you can get local warming. So it's very exciting for those reasons. But as well as being exciting, it's unseen. Now, for me, one of the most exciting things was the fact that perhaps half the scientists believed there would be lakes on the surface of Titan. Now, they wouldn't be made of water, because water freezes at those temperatures. They'd be made of ethane and methane, which are gases on Earth, at room temperature on Earth, but liquefy at the temperatures of Titan and would form, some people thought, lakes, and perhaps there'd be an equivalent of a water cycle with evaporation and rainfall, and perhaps streams flowing with waterfalls and things. Now, we knew that Huygens was going there. It had a wonderful array of instruments, including cameras, but it did have some acoustic instruments, and that's very rare. We very rarely send acoustical sensors into space. Now, the acoustical instruments, and I have to be honest, I didn't have anything to do with the design of the Huygens probe. I can't take any credit for that fantastic mission. Yeah. That was them, not me. Now, they had some acoustical instruments. One measured the speed of sound in the atmosphere as they went down, because from the speed of sound you can work out various things of the chemistry of the atmosphere. And the other was a kind of a rangefinder, a bit like a sonar. It didn't form pictures of the surface, but it bounced a pulse to the surface of the planet and back, and that gave them the range. But it wasn't really equipped to listen to the world of Titan. And in fact, we had never heard the sound of another planet. Now, I was thinking as we were going down, suppose we could hear what the surface of Titan was like. And then some sad news came in that we'd lost a Mars probe. And I was thinking, suppose all the other instruments, the cameras and everything else fail, and all you've got left is a microphone that can listen to the landing. Mm-hmm. If it lands with a splash as opposed to a crunch, we know that we've found the first lake open to an atmosphere anywhere in the universe other than on Earth, mm-hmm. which would be great. So I was thinking, that'd be great. But then I caught myself up and said, hang on, you're assuming you would be able to recognize what that sounds like. You're assuming that you recognize what a splashdown is. I thought, well, how do we know it won't be a slump or a gloop or some other noise? That's something alien.
Right.
So I contacted a good friend of mine, Paul White, at my institute, who does signal processing, and the two of us started looking at this problem, and we started trying to predict the sound of a waterfall, well, a methane fall, a splashdown on Titan. So we did that. And it turns out that it doesn't sound like it does on Earth. It sounds a little bit different, more metallic, but it's recognizable. So he said, great, you could recognize it's a splashdown. So then I said, okay, suppose it lands and the camera's looking that way and the waterfall's behind it. Now, if it had a listening microphone, could it tell what was behind it, this methane fall, just from the sound? Which again raises the question: can you recognize the sound of a methane fall on Titan? So we went back to our equations and computers, and we made the sound of the Titan of the methane fall on Titan. And sure enough, it sounds more metallic than it does on Earth, but it's recognizable. So he thought, that's great, that's fun. And then the guys who actually worked on Huygens did a great job of taking measurements. The probe lasted on the surface far longer than we thought. It was a huge success of the mission, but still we had never heard the sound of another world. Yeah. So I looked at a few more acoustical problems to do with how we might explore the Jupiter's moon Europa, which has an ocean that is vast. In some ways, it's like our Arctic in that it's got a layer of water ice surrounding, overlying a layer of water, liquid water. But whereas in our Arctic we've got perhaps 2 meters of ice overlying a kilometer of water, on on Europa it's vast. It's 20 kilometers of ice overlying 100 kilometers of water. So acoustics obviously present a great way of exploring that, and it's liquid water, so it's obviously very exciting in terms of the potential for life. I don't want to say there's going to be life or anything, but it's very exciting for that. So we did some work on that. But then I was aware, I've got kids. I go around schools and I talk to kids, and I wanted to get them hooked on acoustics for a very simple, from a simple, understandable viewpoint. So I started trying to say, okay, let's to hook kids in. Let's see if we can calculate what the soundscape of some of these planets would be. So Paul White and I got a couple of MSc students, Benoit Burgess from France and Nikhil Banda from India, and they worked with us, and we started calculating the sounds of various things. Dust devils on Mars, lightning on Venus and Mars, this kind of thing. But this built on an earlier collaboration I'd found with a wonderful chap called Andy Petkulescu, who's at the University of Louisiana at Lafayette. Now, I'd done this work on Titan, and I came over to the States, and I was at a meeting, and Andy had been doing work on just the physical properties of these atmospheres, how they, the speed of sound of them, how they absorb sound. And I went and saw him give a talk, and I thought we could put his ideas and mine together, and we could work out what voices sound like on these worlds and musical instruments. It's a real possibility. So, I saw his talk, and then I collared him afterwards and got a couple of beers, and we must have talked just straight for hours. It was one of those magical moments in science. You got a couple of beers, lots of ideas. Of course, we live very far
beers
apart.
And ideas, yeah.
His ideas. So we did this whole program without ever meeting again. We just had those couple of hours, then we did it by email, internet. Yeah. And what we worked out was how voices would sound, because I thought this is the way to get kids interested. We know for 2 reasons. We're very good as humans on picking up clues from language, from voices. It's a big thing we listen to. It's the thing we pay attention to when we're babies. It's the language we learn. We're excellent at picking up clues from that. So there's a lot to be done on it. But also, the other way that it's nice and educational is obviously with scientists, we make predictions, and then we go and test whether those predictions are right. And if they are right, we don't say the theory was right. What we say is the theory's good enough for now. There's no observations that we've done that tell us the theory is wrong. We know all theories are approximations. In a way, all theories are wrong. But there's nothing that we've measured that contradicts that theory, so we'll go with it for now until a measurement comes in. Or, if we make the measurement, we say, well, that's good. We now learned something that we didn't know when we made our theory. We'll put that into our theory and make it better. And so we've learned something which is very satisfying as scientists. And that's a very healthy process. And the only way it ever goes wrong is if a scientist loves the theory that they've made and they'll defend it to the death. That's unhealthy. You don't want that. No. But so long as the scientist is willing to be as eager as the next guy to smash the theory and adapt it, then to meet the facts, then that's great. Now, most of that process of a scientist is spent in that gap from making a prediction to testing it and making the observation. But that's almost an invisible gap. The public don't see that. Yeah. What they generally see is when we've proven a theory. And if a scientist makes a prediction and it's contradicted by theory, by observation, then I think there's a public perception they failed. And in fact, some people they lose their jobs. You were talking about these guys in the Faster Than Light labs. I don't know the details there, and everyone wants science to be done rigorously, but it's pretty tough when every year we hear of high-profile scientists who have to step down because their predictions were not proven right when they get all the facts in.
When they've done the science
nature
right
science. That's where we are. Now, this study was great for telling kids and educating them about the fact that most of the science is spent in that. Because in this case, we can't go to a laboratory and make a verifying measurement. We can't, we have to wait 10, 20 years for somebody to go to another world with a microphone and take measurements of lightning and thunder and whirlwinds on Mars and cryovolcanoes on Titan and see whether we got it right. And we've got that gap. Obviously, the one thing that we did that people won't be able to predict is the voice, because we know as well as the next person that you take your helmet off and your voice, you'll die. But that was almost that's why but it was that fact, I think, that grabbed the audience, that got kids thinking, because you'd have to be crazy to predict the sound of voice on another world when you know you die. It's out of the box. It's the way of thinking you haven't thought. How would you speak another world? You wouldn't model it because it's impossible. But it's that impossibility that grabs people. They think, hang on, this is impossible, but it was done. And the science behind it is as rigorous as we can make it. We publish and all this. And the actual science is also used for other things. We use the findings to help design acoustical equipment. We know if people send microphones to other worlds, we want to use the same basic physics to make sure those microphones are well designed and will work. If we want to send ultrasonic sensors for wind speed and things, we want to make sure they're well designed and so will work and give us accurate readings. And so the science helps that. But it's the voice that really grabbed the school classes that I talked to. That was what they wanted to work on. So we eventually decided what we'd do is we'd like to make this into a kind of real-time voice transform, a thing that will transform the voice almost real-time. It takes a few seconds. And then we contacted, it wasn't the British Museum, it was a local planetarium, Intech, at Winchester. It's a town near us. Used to be the capital of the UK, of England, many years ago. And we talked to them, and I was really pleased because I kind of broached it to them thinking they might think this is crazy, and it was like throwing a ball to somebody and then them catching it and juggling it. They were really enthusiastic about putting it into a show. And so they have now incorporated the sounds into a show in their planetarium using the software that we've given them. And they had the first show yesterday and more shows today. That was great. They were sold out. And I was in the audience, and we were very happy when they did the voices from Venus, and we got a laugh from the kids, which was great. But then the kids come up to me and say, why does the voice sound that way? And the fact is, the physics is intricate, but understandable, and you can explain it to a 12-year-old as to why the voice changes that way. And so that's why I kind of really love this topic of voice changing as a communication tool.
I think it's great. So let's listen to a couple of these samples. We're at the end of the show, so I just want to get these samples in here. So let's listen to the splashdown of a probe on Titan, what you put together. Oh, that's interesting. That was a fascinating sound. And so let's listen to the same splashdown here on Earth.
They're not that dissimilar. I mean, the one on Titan is more metallic. This is Titan. Yeah.
It is more metallic. It's more. There's like some kind of a deeper sound to it. There's yeah.
But the fact is, it's recognizable, which is what I wanted to do, because I'd caught myself short saying, "Hang on, I'm assuming I can recognize this sound." Yeah. So it is recognizable.
Yeah. And let's listen to the sound of the voices. So the recording of a voice on Earth, you've been listening to us, but let's play the recording so that we can compare it against what it would be like on Venus.
Mary had a little lamb, its fleece was white as snow, and everywhere that Mary went, the lamb was sure to go.
Mary had a little lamb, its fleece was white as snow, and everywhere that Mary went, the lamb was sure to go.
It's a little menacing or ominous sounding.
Well, yes, and kids, they love it because their voices are quite high-pitched, and they're quite small, and it changes them into some kind of Darth Vader, so they enjoy it very much.
Yeah, it's the opposite of helium.
That's right. That's right. Yes.
Yeah. And then I love waterfalls, so let's finish this segment with the sound of a waterfall or a methane fall on Titan. It sounds digital. That's just it. That's such an.
It's certain frequencies are kind of filtered out and don't get generated, and so it does give it a more. It's recognizable, I think, as a methane fall or kind of waterfall, but it's not the same as Earth.
Yeah, definitely not the same as Earth. Thank you so much for joining me today. This has been absolutely fascinating, and thank you for staying up late to be able to share your knowledge with us here, here on the show. Everybody, Professor Tim Leighton, he is from the University of Southampton, and you can find his work if you go to the university's website, the Center for Ultrasonics and Underwater Acoustics, and there is some other interesting work that he's done on the sound of, what goldfish hear. Do they really understand? This is other work that you've done with your students. I love what you're doing. This is just fascinating. So thank you, and have a wonderful evening.
Thank you very much. Good night.
Good night. Everybody out there, that does it for the Science Hour. Thank you so much for joining me this week. Next week, I'm taking a week off. I'm going to a conference in Boulder, Colorado, so there will be no Science Hour next week, I'm sorry to say. But we will return on I believe, April 19th, and have a guest to talk with us about anesthesia and consciousness, what we're learning about consciousness from anesthesia. Looking forward to that interview, and I hope that you will join me in 2 weeks for Dr. Kiki Science Hour. Until then, you can always follow what I do through social media. I'm Dr. Kiki on Twitter, Facebook, Kiki Sanford on Google+. And if you need more science-y goodness every week, you can also check out the Science Chat on Justin TV on Fridays from noon to 1 p.m. Pacific time, which probably is not going to happen next week either, or This Week in Science, which is here on the TWiT network at 7:30 p.m. Pacific time on Thursdays. Thank you for tuning into the Science Hour. Really, all I ask for is this 1 hour a week, and I do hope that this hour makes your world a whole lot more interesting. And now for your science meditation of the week.
Physicists at UC San Diego have produced the most detailed images ever seen of a new property of matter called spontaneous coherence in excitons. The images were produced in a basement laboratory where the scientists cooled samples of gallium arsenide to temperatures near absolute zero, then hit them with laser light to produce particles called excitons. As these particles cool down, they form condensates and emit light, which the physicists sent through a complex series of mirrors called an interferometer. When excitons are cooled, they self-organize into an ordered array of microscopic beads, much like a miniature pearl necklace. Within this condensate, the physicists discovered spin textures and phase singularities that are characteristic of this new state of matter. These features will add new insights into the quantum properties of matter, and in time should lead to the development of novel exciton-based computing devices. For more on this discovery and other news in the physical sciences, go to physicalsciences.ucsd.edu.